Hi. So I'm hoping this is going to be the first video after a few failure runs yesterday. And the first thing I'm going to look at is differentiating log and exponential functions, which would be the first lesson of this week. So I'm going to start off with the things that we're expected to know to be able to do this. So the first one is the rules of the derivatives. Now, these are in your formula booklet, so you don't have to memorise them. And in your formula booklet, it tells you that if f of x is e to the x, then the derivative of that stays the same. So that's one rule that we're expected to know about. The other one is if fx is ln x, then the derivative is 1 over x. And you're not expected to know those off by heart. They're given to you in your formula booklet. And the proofs of them are quite a bit off the SL and arguably even the HL syllabus, actually. So you're not going to get to see the proofs of them in this course. You do just have to believe them, I'm afraid. Okay. Now, the other thing that we need to know if we're going to be working with logs and exponentials, and we've done this before earlier in the year, is the log laws. And again, those are in the formula booklet. So they look like this. So, for example, that log A plus log B is log of AB, and of course that works just the same thing if we're using natural logs. Yeah, it's exactly the same rule. The formula booklet writes log log, but it works for the natural log ln as well. And then the ones that go with it are the log A minus log B is log A over B, and that if we have log x to the n, we can write it as n log x. So we've done these before, but we haven't used them in a little while, apart from perhaps in some revision questions. So these are the facts that we need to know to be able to do today's questions. So I'm going to look at the examples on the right, because although we can differentiate just e and just ln x, our questions tend to be a little bit harder than that. And what we normally get asked is to differentiate ln of something or e of something. Actually, I'm going to add another one right at the start, a slightly simpler one. I'm just going to put e to the 2x to begin with. So if we're going to look at some examples, a lot of the examples when we're differentiating these kind of functions use the chain rule. And remember from before, we've done the chain rule, which I have taught you to do by inspection, but also the product rule and the quotient rule also exist, and they are in your formula booklet. But we're going to start off with just some chain rule examples. So if I was differentiating this function, e to the 2x, now the formula booklet only has the derivative of e to the x, and what this is a composite function of that. It's one where our outer function is e, but we have an inner function of 2x. And if we go back to when we first did calculus using this inspection method, when we were kind of doing a shortcut to the chain rule, what I taught you to do was to differentiate the outer function first and write it down. So in this case, if I differentiate e, it stays the same, and I write it down. Then you look at your inner function, you differentiate that, and you multiply by it. So in this case, the derivative of 2x is just 2. I'm going to multiply by 2. And then my final answer, if I write it in a slightly nicer way, would be 2e to the 2x. So we're using that chain rule example mixed in with the laws to differentiate, in this case, e. And I can do something similar with ln. So the second question I'd written up there for myself, ln x squared plus 7. And let's call it f of x. ln of x squared plus 7. So, again, we've got this inner and outer function, but this time our outer function is the ln, and our inner function is this x squared plus 7. So if we do the outer function first, I nearly always do the outer function first. The rule for differentiating ln was this one. So ln goes to 1 over. So this would go to 1 over, but not 1 over x, 1 over x squared plus 7. And I've just realised I was a bit naughty in my first question. And I did the same thing here. I should call this f dashed of x, so it's clear that I was differentiating. So I've done my outer function, ln went to 1 over. Now I need to look at my inner function, so the x squared plus 7. So the derivative of x squared plus 7 is 2x. And again, to finish, I'm going to simplify. So 2x over x squared plus 7. So let's look at a few more. I'll look at b. So b ln e to the x plus 3x squared. Okay, so in all of these questions, there's probably going to be some application of that inspection method. So again, here we have ln as an outer function, and then ex plus 3x squared as an inner function. So to start off similarly again, we're going to start by differentiating the outer function. So ln goes to 1 over. So 1 over e to the x plus 3x squared. And then the inner function, we're going to multiply by the derivative of that. So we've gone e to the x, which stays the same, and then we're going to have 6x for the derivative of that part. And again, we're going to finish by writing it in a slightly nicer way. And don't be tempted here to start cancelling things that you're not meant to. So we don't want to cancel that e to the x and that e to the x, because we haven't got an e to the x in every part of that expression. And in fractions, we can't just cancel one little bit of the denominator with one little bit of the numerator. So we do not want to do that. We cannot simplify this answer any further. So let's get on to some slightly trickier ones now. So I'm going to look at C next. So here we have fx equals x cubed e to the 2x. So now we haven't got an immediate application of the inspection rule. It's not x to the power e to the 2x, or it's not e to the power x cubed. What we've got is two functions multiplying. Yeah, this is the product of x cubed and e to the 2x. So we need to use our product rule. And that means we call the first thing u and the second thing v. Then we need to differentiate both of those. So u dash is 3x squared. And then v dashed. Now we did e to the 2x earlier and we saw it was 2e to the 2x, but we'll do it properly. The outer function is e, so that goes to e to the 2x, stays the same. And then the inner function, we look just as the 2x bit, its derivative is 2, and we'll write that in the front. Then the product rule says we need to do u times v dashed plus v times u dashed. It actually doesn't matter what order because there's a plus in the middle. So the derivative here is going to be x cubed times 2e to the 2x plus e to the 2x 3x squared. Now I've written it there in not a very nice way. So let's write it in a more typical way. We would usually at least put the numbers in the front, and then I would probably put the x's and then the e terms. And we could here, if we wanted to, we could factorise part of this. So I could put x at the front and e to the 2x, because that's in common in both expressions. And that would leave me for the first part a 2 and an x squared. Actually, we can take a full x squared out, sorry. So that would leave me with just 2x and then 3 in there. We don't have to do that unless there's some reason. Perhaps we wanted to solve this equation equal to 0 because it was a stationary point. Then we would be doing what I've done here, because now we could set 2x plus 3 to 0 and we could solve for that. But unless you're asked to, you don't have to do that. It might sometimes be a show that question. So we can mix logs and exponentials with things like the product rule. So let's look at D to finish. So for D, f of x was ln of x cubed e to the 2x. Okay, now, so one thing we can do here is we can do the same approach we've been using already. So that would be saying, well, we have ln, it's an outer function, and then we've got this inner function here. So that would mean we were doing ln would go to 1 over. So it would go to 1 over, in this case, x cubed e to the 2x. While the inner function, we want its derivative. Now, I've consciously chosen this question because you may have already noticed that the inner function here is the same inner function same function I picked in question C. And that was done on purpose because actually it was quite a lot of work to find that derivative. Yeah, so I've consciously done it so we don't have to do that work all over again. I can just write my answer that I got in part C from my inner function derivative. So x squared e to the 2x plus 3. Now here I can do some cancelling. Okay, because the e to the 2x we've got on the top and on the bottom, and we can cancel, we've got x squared on the top and x cubed on the bottom, so I can get rid of the cube there and get rid of all of the x squared, leaving me with just an x on the bottom, and then that 2x plus 3 on the top. So we had some simplifying here to do at the end. Now, suppose that I hadn't already done that part C. So I'd have had to do all of this work as part of this question D. And that's not very nice to do, but we could have been a little bit smart with our log laws, and we could have done it this way. So I'm just going to write the question again. So fx is ln of x cubed e to the 2x. So if I go back at the beginning I wrote some log laws. And the first one I wrote down, I'll use the ln version of it, was this guy. The ln A plus ln B is ln AB. And we're actually going to use that law in reverse. We're going to start with ln AB, and we're going to say we can write it as ln A plus ln B. So that becomes down here. So it's like thinking that this is the A and that this is the B. So I've got ln x cubed plus ln e to the 2x. And I can go one step further than this simplifying. So already we've made our life simpler, because now I've just got ln of x cubed and ln of e to the 2x, both of which I could differentiate using the inspection rule. But I can go one step further and I can bring the powers down to the front. So again, I'll go back to those log laws quickly. This one here says if I've got log and then my base, so in this case I've got an x and I've got an e to some power, I can bring that power down to the front. So I can make this 3 ln x and 2x